order differentiation means that we need to find the higher order derivative. And when we talk about higher order derivatives, we're not simply taking the derivative of a function, but we're taking it to a higher step, meaning we will be differentiating repeatedly. The question would be how many times, and it depends upon the problem. If the problem says that you need to find the second order derivative, then you will be differentiating twice. If the problem says you need to find the sixth derivative, then you will be differentiating the function 6 times. So I think that's an easy concept to understand, but let me just give you the notations that we use in higher order derivatives. So we usually represent them as we usually use to represent the derivative as y prime. So this is the first derivative. But if you would ask me about the higher order derivatives for this Lagrange equation, notation, then we could say that the second order derivative would be y prime prime, and then we have also y 3 prime for this third derivative. But of course, I wouldn't recommend you to if it's the 10th derivative, then you'll be doing something like 10 something like apostrophe here. So you'll be writing something like a close parenthesis and then the number inside. So that means that you need to take the 10th derivative of that function. If we will be using the if it is f of x, then the first derivative would be f prime x, the second derivative would be something like this, and then the third would be 3 apostrophes. You can also write 3 here, and then for, let's say for example, at the end derivative would be f to the n x with the close parenthesis. Now this is the Lagrange notation, but we can also use the Leibniz one. So if we want to find the derivative of the Leibniz, the first one will be this one, and we have this function f of x. The second derivative for this Leibniz notation would be something like this, and then this one is f of x. So it's like the function is f of x, then take the second derivative. Now I have to emphasize that the square here would be for the numerator, and then the square would be for x for the denominator. So don't get confused, because if you write something like this, then for some reason it will be something like dy over dx and then quantity squared. It will be confused with this, and these expressions are different from this one, since where you're actually taking the square of the first derivative, not the second derivative. So let's remove it so that I won't get confused. Okay, so the third derivative would be something like d cubed y and then dx cubed. That's for f of x. And then if you have n, then you will just simply write n here, and you don't have much problems since we're using the the Arabic numbers. So that's it for our Leibniz notation. So this is fairly almost all the notations that we'll be using, and this usually actually appears on differential equations, and we'll be using both just to give you an idea of how it works. So for Newton's notation, we also have something, we used to express this something like d sub y or d sub x. So it depends upon the function that you'll be differentiating. So if we wanted to differentiate the function y, so you'll be using this dy, so that is d and then something like y, and then just raise this to a certain derivative or order, and that will be the higher order derivative of that. For example, we have y equals 3x squared, and then you roll something like d squared and then y, so that means that I will be taking the second derivative of this y, which is equal to 3x squared, of course with respect to x. So now that I've already given you the notation, let us try to solve problems involving higher order derivatives. I'll be taking the one that is written in your module. So you have there the functions here, f of x, and one here would be the g of x. And it says here, of course, the problem would have to specify what particular order of derivative that you need to take. And in this case, we only have one here for the first, then second for the second one, and the third and fourth will be just the first. The first derivative, and this one is the second. So let's try that for practice, and probably we could give you some more complicated. So for the first one, what we have here is f of x. So if we take the first derivative, that's just simply f prime of x, and then we use the trigonometric property to evaluate this. So that's sine, so the derivative would be cosine, and then just copy what's inside. So that's a b x, and then of course the square of this. And we're not yet done, since we'll be using chain rule to evaluate what's inside. So we take the derivative of the inside, multiply it with our first differentiation rule. So we have here sorry, I forgot c, abcx, and then quantity squared. So in this case, we have something like a function that is squared. So the derivative of that will be, using the general power rule, we have 2, and then abcx, and then minus 1, so that will be 1. And then the derivative of what's inside this general power rule, so that is simply abc, because abc is a constant. So if you would rewrite this, we have f prime x equal to 2a squared b squared c squared, and then x, and then the cosine of this abcx, and then squared. So this is the derivative of our first problem. And we're done with that, since we just need to take the first derivative. So let's move on with the second one. So we need to take the second derivative of that, since we have two primes here. So the first derivative of this function is equal to, remember, this a to the b is a constant, and x to the c would be the differentiating variable. So the variable we need to differentiate. So we have a to the b, just copy it, and then by constant multiple rule, so the derivative of x to the c would be c, and then x raised to c minus 1, and then plus, we copy 2, and then the derivative of x to the c would just be c x to the c minus 1, then minus 3a. The 3a would be just a constant, so the derivative would be 0. So let me just rewrite this first before we differentiate again. So we have a to the b, and then c x c minus 1, and then plus 2c x raised to c minus 1. Could also rewrite this as x raised to c minus 1, and then c x raised to c minus 1, and then factor this out the constant, so we have a to the b plus 2. So we can also write that in that form, but what we have to do here is to find the second derivative. So we'll be finding the second derivative for this, and let's just use this one. So since a to the b plus 2 is a constant, I'll just be copying it as well as with c. So we have something like this. So that's a constant, and then I just need to differentiate this x raised to c minus 1. So I'll be getting c minus 1 here, and then x raised to c minus 2. So the second derivative would be equal to c times c minus 1, and then a to the b plus 2, and then x raised to c minus 2. So that's the second derivative. And if you would be noticing this, this c and then c minus 1, it all came from a single exponent from x, which is c. So for your higher order derivatives, you will always be noticing something like an exponent decreasing by 1 unit, by 1. So that's a good pattern that you can use so that you can check if your answer is actually correct. So let's just box this and move on to our So this is just the first derivative. I will not be doing this. You could just review your differentiation rules and then just take the first derivative. I'll just be doing this g of x since it has a second derivative. So g of x is equal to x to the b minus 4 and then plus 1 over x to the a plus c. So in this case, I would be taking the first derivative, and that's just b minus 4 general power rule, so x raised to, or just power rule, and then b minus 5 since I subtracted 1 from the exponent, and then added with, so this one I can actually write this as x to the I can actually write the last term here as x to the a plus c raised to negative 1, just to simplify our differentiation, since by quotient rule that would be, more tedious than using this exponent raised to a negative. So I'll be using this one. So we get negative 1 here, and then just copy what's inside and then subtract 1 from this, so we have negative 2, and then take the derivative of what's inside, so that is x raised to a minus 1, and c is a constant, so I won't be taking the derivative since it's 0. So we have b minus 4 and then x raised to b minus 5, and then minus, that's I think that's a x raised to a minus 1 all over x to the a plus c, and then that's positive 2 since it's already at the denominator. Okay, so that's the first derivative. Now we're not yet done. We need to take the second derivative for this. So the second derivative would simply be b minus 4, and then just bring down that power and then do power rule. So that's b minus, so 5 minus 1 would be 6, so x, and then b minus 6, and then subtracted with, now we can do something like quotient rule here. So that's x to the a plus c squared, and then the derivative of the numerator would be a times a minus 1 and then x raised to a minus 2. So that's actually just the the first term, g of x and then f prime x. So that's just it. So we need to subtract this by the second term. That will be minus. Now let's move a little so that you can see it. So minus, that's a, and then x raised to a minus 1, and then the derivative of this would be 2, and then x to the a plus c, and then we're not yet done. We need to take derivative of the inside, so that's a and then x to the a minus 1. Okay, and then we need to divide all of these by the square of our denominator, so this one will be to the 4th. So we can also do something like simplifying for this. So let me just simplify for you. So I won't be requiring you to like FOIL this. Let's just leave it something like 4 and 5, and then x b minus 6, and then this one, I think you can just factor out the terms that are the same. So you can factor out x to the a plus c here, so that we can have 3 and then 1 here. So that's minus x to the a plus c, and then a times a minus 1, and then x raised to a minus 2, and then minus a, and then actually I'm seeing another factor that we can do. So let's write 2 here, and then it will be cancelled out, so I'll be left with a x raised to a minus 1, and then divided by x to the a plus c, and then they should be 3. Okay, I can also factor out this x to the a minus 1, since I think that would be x to the a minus 2, but Of course, you're not required to do that. You can also leave the answer like this. I mean, I'm after your differentiation skills and not your simplifying skills. So whichever suits you well, then take that as your final answer. I'll be taking it. Okay. So that's all for g of x. And let's just box this so that you know the answer. So anywhere here can be an answer. But of course, if it's very evident, you can simplify that. Like for example, this x to the a plus c. It's very evident to cancel out x to the a plus c. So might as well want to do it. So that's it for the basics of our higher order derivatives. And now let me just give you some example here. Let's try doing something like the derivative. Our function is y equals cosine of x. Okay, and I need you to find the first derivative, and then the second, the third derivative, and the fourth derivative. Okay, so let's do it. So if you take the first derivative of cosine of x, that's negative sine of x. And then the second derivative would be negative cosine of x. The third derivative, so we differentiate this negative cosine of x, that's sine x. And then the derivative of sine x would be cosine of x. So for periodic function, like trigonometric function, what you can see here is that for periodic function like cosine and sine, the derivative would be repeating itself at the fourth. Okay, so for every fourth derivative, the given function would repeat itself. So remember this cosine, and then this one is cosine. So that's a good way to check. For example, I need you to find the 100th derivative of these functions. So what is the 100th derivative of cosine of x? So remember, this is the 100th derivative, and for every fourth derivative, you would have cosine of x again. So you might as well want to like divide this by 4. What you'll be getting is 25, and 25 is, 4 is divisible by 100. So in that case, the answer should be cosine of x, since basically at the 25th fourth derivative, we're at the 25th fourth derivative, so that's cosine of x. But what if I wanted to like ask you what is the 89th derivative of this cosine of x? So you just have to like divide your 89 by 4. So in that case, the closest possible that you will be getting is around 22, and 22 times 4 is actually 88. So in this case, at the 88th derivative, so if I have something like the 88th derivative, that is just equal to cosine of x. And if this is the 88th derivative, which is cosine of x, you start with this, and then the 89 would be negative sine of x, because you're just simply one step again. Because after this fourth derivative, the next one would be this again, and then it's just the cycle of this. So if the 88th derivative is cosine of x, just differentiate it and you'll be getting the negative sine of x. So that's how it goes for the higher order derivative, which is very, very high. Okay, now let's try number 2. What if we try to like find the derivative of let's say sine of 2x, and then let's try finding the, let's say, 76th derivative of this sine 2x. So remember, this sine 2x would just I want you to like do something like take the fourth derivative of this for a periodic function just to see the trend. And if you take the first derivative, you have cosine of 2x, but instead of just writing cosine 2x, you also have something like 2 here because the derivative of 2x is 2. Now for y prime prime, or the second derivative, you have something like 2 cosine of 2x, and then we multiply again this with 2, since we have to differentiate what's inside. And then when we try to like, this should not be cosine, but it should be sine, and that's negative. Okay, so if you take the third derivative, that is, so I will not be multiplying this yet. I'll just be rewriting it just so you can see what happens. So the derivative of sine, or negative, so just copy the negative here. So the derivative of sine is cosine, and that will be negative here, but there's some 2 here again, since the derivative of 2x would be 2. And then for the fourth derivative, so that is equal to, the derivative of cosine is negative sine, but since this one's negative, so it becomes positive. So we have here sine and then 2x. And then I'll just be copying these constants that we have before. And then we have some 2 here again, since we need to take the derivative of what's inside. So as you can see here, the final derivative would be 2 raised to the fourth and then sine of 2x. So that's basically what happens when you take the fourth derivative. So as you can see that here about the trend of this graph, the function, if you have a constant here, let's say the constant is c, at the end of the differentiation process, where you have to take the higher order derivative, the value here is actually equal to c raised to the order of our, let's make the order of our derivative expressed as d. So it's like, you have a constant here that is 2, and then you raise that to the order of differentiation, and you'll be getting the value of your coefficient here. And then the cosine of 2x, just take the cycle of this cosine 2x, the differentiation process, and then you'll be taking the sine of 2x. Okay, so this one, the sine 2x, so it's sine 2x here. So the clue here is that if you have the 76th derivative here, and as you can see in the pattern, the coefficient here starts with by taking the number here associated with x and then raising that to the order of differentiation. So with that, the coefficient here should be 2 raised to 76, since that's how it works, because the first derivative, you'll be plugging out 2 from this 2x, since that's the derivative. So by doing that 76 times, you'll be having 2 raised to 76. And then you'll be applying the cycle of sine, so it's 76. So if you take if you divide 76 by 4, that's actually 19, and 19 is a whole number, so that's divisible by 4. So with this, your answer should be sine of 2x again, since that's the fourth derivative. Had it been something like 75, so you'll be using 2 raised to 75, and then you divide 75 by 4, that's actually 18.75. So at 18, you have 18 times 4, that is actually equal to 72. And 72 would be something like the fourth derivative. Actually that's the 18th fourth derivative of sine 2x. So if you have 75, that's plus 3. So you start with sine, and then the first derivative would be cosine. So this one is cosine, that's 1. This one is 2, so that's 1, that's 2, and then this one is the third. So you have cosine of 2x, and negative, so that's negative, and then cosine of 2x. So this is for the 75th derivative, and this is one for the 76th. Actually, you can check it out. So if this is the 75th derivative, that's 2 to the 75, then you differentiate this, that this should be the answer. And that's correct, since, differentiating this cosine would be negative of sine, and we have here negative, and then just multiplying this with our 2 would make the exponent larger. So that's how it goes for this kind of function. And let's have another one. Let's take, for example, number 3, and then I have here y. Let's have another. Let's say the fourth derivative of, let's say, x cubed plus 2x squared minus 6. Okay, this is fairly easy one. Now to do this, let's since it's just the fourth derivative, let's have from 1 to 4. So we have here 3x squared and then plus 4x, and that's the first derivative of this function. So we add something like the x here just to have this. I mean, it should have some dx since we're taking actually the for the first derivative. And so now let's take on the second derivative. That would be 6x plus 4. Now the question would be, how do you write this dx in its way in a form that is the second derivative now? So what I'll be, you might be thinking that you could write this as dx squared, but technically it's meaningless since we used to write this Leibniz notation in a way that the differential equation can separate these two variables, dy and dx. So it is something like not improper, but less common to see something like the x squared and an equation just standing all alone. It would be meaningful if you would have something like dy squared over dx squared, but since this is expressed in a way that this Leibniz notation, what I can do here, or what you can do here, is to simply rewrite this as if this is the second derivative of dx. So that will be something like d of dx and then just take the dx. That means that you take the derivative of dx. So that's it for that's a way of writing this dx instead of writing dx squared, which is it's much less common to do that. So by the way, it's just a notation for dx. It just gives you the idea that we need to take the derivative of this as well, but our main concern is this one. So we have the first and then the second, and then let's have the third derivative. So that will be 6, and then you can just simply write d squared of dx squared, and then use some dx here. So that's it for the third derivative. So but we need the fourth derivative here. So if we take the fourth derivative, then the derivative of 6 would be 0. So in this case, 0 is our answer for this. And actually, if that's easy since we have something like polynomial function here, and basically you just have to take the derivative and that's all. But what if I gave you something like d, and then let's use y. So y equals x to the 1078 and then plus 36 x to the 546 and then plus 4. So what if it's like this? It's an exponent that is very high. And then I wanted you like take the let's have something like, let's take the 1000 the 1100 derivative of this. So what will be the 1100th derivative of that? So when we approach this problem, something like this, what you have to do is, if we have some polynomial function, so that's the p of x that we have, you should be inspecting the exponent of each term and then the order of differentiation. If the order of differentiation is, it's greater than the exponents, so let's say m is the exponent, then your answer would be automatically be 0. Okay, so why is that so? Well, since we've already noticed here that if it is x cubed, it becomes 0, because the only way that we can approach is that the answer here would be something like, it can only be differentiated in a way that x would have an exponent that is at the first degree. And To do that, you just have to like differentiate this 1078 times just to give you the final, x that will be, the final derivative of x that will be equal to 1. So at the, let's say, the 1077th derivative, you would have something like the constants here and then x raised to the first degree. So that's around y to the 1077. And then doing something like 1078 would give you another constant here, and there's just all the constants. So any derivative past 1078 would give you a value that is 0, and 1100 would be, it's larger, so that would be 0. And the same thing goes for 546. So had it been something like the derivative of 546, then we would be having some constant here and then the value of this. Okay, so as you can notice, that is fairly easy if we have a derivative that is, the order is greater than our exponents that we have in our polynomial function. And that's a different story when we have the quotient rule, and we won't be able to find it actually. So anyway, so that's a good way of finding the derivative. But what if the order of differentiation is actually less than the highest exponent here, or the exponent of our polynomial function? So let's try doing something like y. Let's start with discovering the pattern. So let's have y equals x to the, let's say, 6th, and then minus 4x probably. So I need you to take the 5th derivative of this. So let's start with the first derivative, that is y prime is equal to 6x to the 5th. The second derivative would be, for the sake of this problem, I will not be multiplying, but I'll just be rewriting this as multiplication. So that's 5 and then x to the 4th. By the way, this should be minus 4, and then it becomes 0 at the second derivative. So that's what it meant by this 5 is higher than this one, so automatically it will be 0 at the end of this differentiation process. So it becomes constant at the first derivative since this is just 1. So anyway, so let's move on. The third derivative would be 6 and then times 5 times 4, then x cubed. Now you take the fourth derivative, that is 6, and then times 5 times 4, and then times 3, and then x squared. We take the fifth, and then that's the final answer would be 6, and then times 5 times 4 times 3, and then times 2, and then x raised to 2 minus 1, that is x. So this is the derivative. We can also do some multiplication here so that we will have an answer that is, it's just one constant representing all of these. So the answer would be 720x. So it is easy if we would have something like at least the fifth derivative and a typical x raised to a certain exponent of a real number. But what if it's not like that? So what you'll be having is, by the way, I would have to specify that this m is actually a positive value. That's the same way as this one. So m here should be positive, because that's another story if it's negative. Okay, so by the way, so let's go back here again, and then what you can see here is that if we need to take the fifth derivative that is less than m, what you will be having is something like, if you can remember your statistics, this is something like 6 times 5 times 4 times 3 times 2, and that's actually factorial. So if you have something like the derivative of this and it is less than m, what you have to do is to have the coefficient as if they're written like n prime, or the n prime, n factorial. That is, the exponent of this is 6. If you take the 6 factorial, then that will be 6 times 5 times 4 times 3 times 2. That's the coefficient. And then divide this by n minus d and then factorial. So that simply means that if I have exponent that is, let's say, 6, I would have to subtract that with or by the order of differentiation, that is 5. And then that's the exponent of our function and then write the function, let's say x, and then raise that to a certain n minus d. So that's how it goes for our general power rule that we have. So instead of, just having this n, what we have is something like this. And let's try something like y is equal to, let's say, x to the 18 minus 4. Let's say 2x and then 4x to the fifth. So I want to take the let's say the fifth derivative of this. So if we would take the fifth derivative of this 2x to the 18, you could just copy 2 since it's a constant multiple, so you don't have to worry about it. And then multiply this with 18 factorial, divide this by, that's 18 minus 5, so that is 13 factorial, and then x raised to 18 minus 5, so that will be 13. So that's the coefficient of this, and then that's the constant multiple. And then how about this 5? So in here the expression is actually d is equal to m. So what you have to do is simply if d is equal to n, let's do some d is equal to n. So d is equal to n. If you would be substituting that to our equation, that will be minus, and then just copy 4, and then times n factorial would be 5 factorial, and then divide this by let's do this first. X raised to 5 minus 5 would be x raised to 0, and that is just 1. But how about this? N minus d would be 5 minus 5, and that will be 0 factorial. And remember, 0 factorial is 1. So we can now rewrite this as the fifth derivative would be equal to 2, and then that's 18 times 17 times 16 up to 14. So I think I will not be writing that. So let's just leave it something like 18 factorial over 13 factorial. But you can also solve for it. I don't mind, but it will be very long here, so never mind. So this will be negative 4 times 5 factorial. So that's the derivative of this. Now, and 0 factorial, remember, is equal to 1. So this is our answer for this problem. So what you can notice here is that if assuming that our n or m, this is just the exponent of our x, is positive, if it is greater, if the order of differentiation is greater, you can see that it is 0. And also this is true for polynomial function only. So if the order is less than m, you could use this general formula here just to get the factorial of that, and then divide it with n minus d factorial, and then x raised to n minus d, because that's how the pattern goes. So yeah, that's it for our d when we have polynomial functions that are less than or greater than the exponent of our order. So now let's try another. Let's take, for example, this one. So let's take y is equal to x raised to negative 2 plus 4x. And I wanted to take at least the third derivative of this. So now for negative exponents, what we have to do here is to discover the pattern. And I'll be doing this. And since this one is greater than the exponent here, it will be 0 at the end of this. Now let's before taking the third derivative, let's just do something like the first derivative. So that's y prime, and then we have negative 2x, and then raised to negative 3, and then plus 4, and then we take the second derivative, that is equal to negative 2 times negative 3, and then x raised to negative 4, and then plus 0. So the last one, which is the one we need, is the third derivative. That's negative 2 times negative 3 times negative 4, and that is x raised to negative 5. Okay, so that's it for our third derivative. And if we would simplify this or write this in just one constant, that's 4 times 3, 12, and then times 2 is 24. So that's negative 24x raised to negative 5. So what you can discover here is the pattern that we have. If we have something like negative, an exponent that is negative, it just subtracts in a way that it increases its value, but it depends upon the order of differentiation. So it starts with itself, the negative, and then you subtract the rest of the order of that. So in this case, if we have something like n that is, let's take positive n, I mean the absolute value of that is 2, we just have to like add the order of differentiation and subtract it by 1. In this case, we'll be finding that we are representing actually the factorial of these values here, 4, 3, 2. So let's check on that. So if we take the absolute value of n, that is positive 2, and then we add the order of differentiation, that is 3, so 5, and then minus 1, and then factorial. So in this case, we have something like I'm sorry, it's not 5, it's 3 actually. So this one is 3, so that's the order of derivative. So you have 5 minus 1, that will be 4 factorial. And this one is actually the 4 times 3 times 2 factorial. But 4 factorial is actually equal to 4 times 3 times 2 and then times 1. So in the cases where we have something like let's say cube, so in this case it would just be something like from 3, and you need to subtract, divide that with 2. So what we have to do is to divide this by the value of the absolute value of the exponent and then minus 1 factorial. But in this case it would just be something like 2 minus 1, which is 1. So in this case, for negative exponents, what we have is something like the absolute value of n and then plus the derivative, or the order of derivative, minus 1, and then we take the factorial of that and then divide it by the absolute value of n minus 1 and then the factorial. But there's also another problem. We need to know the sign of this, and the sign of the derivative is just fairly easy. You just have to multiply this with negative 1 raised to the order of derivative. So in this case, we would be having negative if it's odd and even if it's, positive if it's even. And then just do something like x and then raise that to the value of n, that is not the absolute value but just n, and then subtract d. Okay, since we don't have any problem with subtracting it. So that's how it goes for our negative exponent. So that's d is positive and n is negative. So let's have something like y is equal to, let's have something like 7x raised to negative 5. And I need to take, let's say, let's have it 15. And I wanted to like take the 10th derivative of this. So what we have to do is just copy 7 and then apply this rule. So what we have here is negative 1, and then we raise that to the 10th power, so that will be even, that will be positive. And then multiply this with the factorial that are here. So that's the absolute value of n, that will be 15, and then plus the order of derivative, that's 10, and then minus 1. So factorial, and then divide this by the absolute value of n, that's negative 15, and then minus 1. So should be 15 and then minus 1. So the factorial that is on the denominator, I would also want to specify again that this is actually what cancels out all the values that should be on the in front of the factorial, or the last terms of the factorial, because factorial means that you have to like multiply this at the end, the very end term of the real numbers, of the whole numbers. So this denominator cancels them out because we have something like a negative exponent. So that's this for this exponent, coefficient, and then x raised to negative 15 and then minus 10. So that's why 10th derivative, and then that's 7 times 1. So that's 7, and then 15 plus 7 would be 15 minus 1. So that's 14th. 25 minus 1, that's 24 factorial, then divided by 14 factorial. And then x raised to negative 25. So that's the answer for this one. You can also evaluate this, but I will no longer do that. But if you want, I could just use some calculator and then solve for this. The answer would be something like 7.18 to the 12 times, just you could also times it to 7. So the answer here would be around 4.98 times 10 to the 13, and then x raised to negative 25. But I would always prefer this one here, since this is the exact answer, and the coefficient here, or the constant, is actually rounded up. So that's in mathematics always better if we represent the answer as if they are the exact answers. So that's it for our negative coefficient. Negative exponent, sorry. So I think that's all for the higher order derivatives. And what you have to remember here is things like that appear in a way that you have to take the derivative not just once, but depending on the order of that derivative. So sometimes it goes more complicated. It can go in a way that you need to find the derivative of, let's say, 2 and then cosine of 2x. This is the derivative, and then plus x to the, let's say, 15th. And I wanted you to let's say 2. And then I wanted to take the 14th derivative of this. So you just have to apply all the properties here. So that's 2 multiplied with 2 raised to the 14th power. And then remember, 14 is not divisible by 4, but 12 is. So that's 2 derivatives from cosine. So the first derivative is negative sine, and then that will be negative cosine. So we have here negative cosine of 2x. And then plus, since this is 14, it is one step lower than 15. So we have to apply the properties here. So we get 2 times, that's n factorial, that's 15 factorial, and then n minus this, so that's 1 factorial, and then times x raised to 15 minus 1. So the answer to the 14th derivative of this would be 2 to the 15th, since this should be 2 to the 14th, but there's another 2 here, so I can just add exponent, and then negative, that's cosine of 2x, and then plus 2 times 15 factorial, and then x raised to 14th. It should be 14, so this should be something like x only. Okay, so that's it for our answer here. So I will not be giving you something like, for example, I have y here, and then x squared plus 4, and then this one is x cubed, and I wanted to find the derivative of, let's say, 56 derivative. So actually this shouldn't be possible. This could be, actually this one could be solved, but you have to redefine this first in a way that we separate this as 1 over x, and then plus 4, and then over x cubed. In this way you can solve for the y to the 56. But if it can't, for example, we have y is equal to sine of x, and then cosine of, let's say, 2x plus 4, something like this, minus x, and then I would ask you to find the 100 derivative. So I won't be doing this, since we don't have any pattern that can, that we can derive from this. So I'll just be using those that we can have something like patterns that we need to observe. So this one can be solved by using this. So don't attempt to derive from the quotient rule. That will take years to do that, since quotient rule is actually complicated. It's not complicated, but the properties that it applies, all the differentiation that you have to undergo, is actually very long compared to doing the power rule and the general power rule. So that's it for higher order, and I'll be giving you some time to ponder on this and then practice it so that you'll be ready for another application of this higher order in limits. So thank you.